Hello. In the previous lecture, we started the process of proving existence of an algebraic closure of a field. We proved the following result. We showed that if I start with a field f, then there is always an algebraic extension of f, let's denote it by E, such that every polynomial in f, every non-constant polynomial in f bracket x, has a zero in this extension. Of course, we want to find an algebraic extension where all the zeros of every non-constant polynomial in f bracket x are inside in this algebraic extension. In fact, we want to find an algebraic extension which is algebraically closed, which means all the polynomials even in E bracket x have all of their zeros inside E. Okay, so this is our goal. We proved this proposition. Let's see how this proposition can help us to show that if f is any field, then there exists an algebraic extension f bar over f, such that f bar is algebraically closed. Remember, a field is algebraically closed if, so there were three equivalent properties. If every polynomial in f bracket x, every non-constant polynomial in f bracket x has a zero inside f bracket, in f bar. So let me restart. F bar is algebraically closed if either every non-constant polynomial has a zero in f bar, or every non-constant polynomial in f bar can be decomposed into linear factors, or there is no non-trivial algebraic extension of f bar. So these are three equivalent properties, and if a field has these properties, we say that it is algebraically closed. Now, for a given field f, we want to find an algebraic extension of f, which is algebraically closed. Okay, so we start with the proposition that we have, starting with f, let's call it f naught. I use the proposition, find an algebraic extension, I call it f1, so that every polynomial in f naught has a zero inside f1. And then I do this again. I find, starting with f1, I find an algebraic extension of f1, we call it f2, so that every non-constant polynomial in f1 bracket x has a zero in f2. And I repeatedly use this proposition and inductively end up getting this tower of fields, f1, f0, subset of f1, subset of f2, and so on, a tower of fields, so that f sub I plus 1 over f sub I is an algebraic extension. And every non-constant polynomial in f sub I bracket x has a zero in f sub I plus 1. Okay, so we can use the proposition and create this chain of fields. Now, we've discussed this before, that whenever I give you a chain of algebraic objects, then the union of this chain should satisfy the same algebraic property. So if I give you a chain of ideals, their union should be an ideal. If I give you a chain of subrings, their union should be a subring. If I give you a chain of subgroups, their union should be a subgroup. Now, here I'm giving you a chain of subfields, so the union should be a field. So let's see why this is the case. So let's denote the union of these f sub i's by f bar. Now, my claim is that f bar is indeed a field, a subfield of subfield. I mean, here I'm not actually viewing them as a subset of a single set. So I cannot say a subfield, but my claim is that F bar is indeed F field. Okay, so, but what is the operations? Every two elements that I take in F bar, because I'm getting a chain, I'm working with chain of fields. You see, every two elements that I give you in F bar, they belong to F sub I and F sub j for some I and j, but without lot of generality, I can assume that, let's say, I is less than or equal to j. And that means both A and B belong to F sub j. Now I can talk about addition, multiplication, division, subtraction inside F sub j. And that is the operation that I'm taking in F bar. And notice that if I increase j, because F sub j is again is a subfield of F sub k for every larger index k, the operations stays the same. So that those are well-defined operations, and all of them belong to the union, because so when they belong to the field, so they do belong to the union of these fields, and that means that F bar is indeed a field. So these are well-defined operations, and F bar is a field. Now next we want to show that F bar over F is an algebraic extension. So I pick an element inside F bar, and that means that I'm taking an element from one of these F sub i's, because F bar is a union of these F sub i's. For every given alpha in F bar, I can find some index so that alpha belongs to F sub I. Now notice here I have a chain of algebraic extensions, F1 over F0, F2 over F1, till we reach to the extension which contains alpha. And we know that when I give you a tower of field extensions, when all the blocks are algebraic extensions, so is the top one over the base. So F sub I over F sub 0 over F is also an algebraic extension. Now alpha belongs to F sub I, so alpha is algebraic over the base. So alpha is algebraic over F. This is true for every alpha in F bar. That means F bar over F is an algebraic extension. Okay, now finally we want to show that F bar is algebraically closed. So we need to start with a non-constant polynomial in F bar bracket X. So suppose this non-constant polynomial is G, and coefficients of G are A sub m minus 1, A sub m minus 2, till we get to A sub 0. So this is a non-constant polynomial in F bar bracket X. F bar is union of F sub i's. This means that for every index I can find some index n sub I, so that A sub I, this coefficient, which is inside F bar, belongs to F sub n sub I. Again, F bar is union of F sub j's. So for every I can find some index, and so I can find some index so that F sub n sub I contains A sub I. Now again, F sub j's or F sub j's are a chain. So if I take the largest index and call it n, the largest involved index, and I call it n, then all these coefficients belong to F sub n. You see, these F sub j's are getting larger and larger. So if n is the maximum of n sub i's, then F sub n contains F sub n sub i's as subfields. So all these A sub i's belong to F sub n. That means the polynomial G actually belongs to the set of non-constant polynomials with coefficients in F sub n. But how did we define this tower? We chose this tower of fields in a way that Okay, so of course this algebraic condition we have used, but the second one says every non-constant polynomial in f sub I bracket x has a zero in the next field. Now here g is a non-constant polynomial in f sub n, so it has a zero in the next field. So g has a zero in f sub n plus 1. But f sub n plus 1 itself is a subfield of f bar. That means g has a 0 in f bar. And that's exactly what we wanted to show. We wanted to show that every non-constant polynomial in f bracket x has a 0 in f bar. Every non-constant polynomial in f bar has a 0 in f bar. And that's exactly what we showed. So altogether, we found an algebraic extension of a field f, and so that this algebraic extension itself is algebraically closed. Such a field is called an algebraic closure of f. I mean, we can change the notation, the symbols of f bar, but we will show that up to an isomorphism, up to an f isomorphism, an algebraic closure of a field f is fixed, is unique. So there is a unique algebraic closure of a field f up to an f isomorphism. So that's the next theorem that we want to prove. So f is a field. Suppose f bar and f bar prime, both of them are algebraic closures of f. We want to show that there is an f isomorphism, let's call it theta, from f bar to f bar prime. So roughly, what we are doing is like this, that we view algebraic closures as a union of a family of splitting fields of polynomials in f bracket x. So as we have discussed, we can start with families. I mean, we can start with a single polynomial that's non-constant in f bracket x, and then consider it's a splitting field, and then add splitting field of another polynomial to this, and continue like that. And we didn't prove it, but it's quite intuitive that that would be our f bar. Now, if we want to find an isomorphism between these two fields, we can use uniqueness of splitting fields up to isomorphisms and then glue these isomorphisms together. So that can be a scheme of proof. But as you can see, we have an infinite family of splitting fields that we need to work with. And we have infinite family of splitting fields, and therefore we have this process that we are introducing has infinitely many parts. And the cardinality of this process is not necessarily countable. If it was countable, we could have used a type of induction in order to construct this theta. But as we have discussed it in the existence part, in order to avoid this infinite process or make it legitimate, we need certain results and assumptions from set theory. So one possible route is using well-ordering principle, not principle, well-ordering theorem rather, and transfinite induction. And the second route that we are going to take is to use Zorn's lemma. So often when we use Zorn's lemma, we avoid using inductive arguments. One can compare the usage of Zorn's lemma in this type of settings, instead of transfinite induction, one can compare this to using well-ordering principle of positive integers in basic number theory, rather than using, instead of using the usual induction. So there is a type of parallel between them. Okay, so now next what we want to do is to use a Zorn's lemma and create this theta from f bar to f bar prime. So often we want to say that this Zorn's lemma is going to tell us that okay, I want to create this map from f bar to f bar prime. Zorn's lemma guarantees that there is among all the subfields of this, there is a largest one that can have an embedding into f bar prime, and then we want to argue that it is indeed the entire f bar. Okay, so let's do the mechanism. Let sigma be the set of all the intermediate subfields of f bar over f. Those intermediate subfields coupled with f embeddings of those fields into f bar prime. Notice that this set itself is not empty because f itself, f comma identity, identity map of f, or embedding of f into f bar prime, is an element of sigma. So sigma is a non-empty set. It does contain at least one element, which is f comma embedding of f into f bar prime. Now, we want to say that we can also find f bar comma theta in this set, and therefore we can embed f bar into f bar prime. So that is our goal. You see, we want to find the largest intermediate subfield possible. So that's our goal. In order to do so, we are going to argue that, okay, so this set does have a maximal element. I have to tell you what the ordering is, but we are going to argue that it has a maximal element. At least the set part is with respect to inclusion. And we want to argue next that this maximal element is of the form f bar comma theta. Okay, so that's the scheme of the argument. Let's see how we can do it. First, I have to give you the needed partial order on a sigma. So we say the pair E1 comma Phi1 is at most the pair E2 comma Phi2 if, first of all, E1 is a subfield of E2, and second, Phi2 is an extension of Phi1, meaning when I restrict Phi2 to E1, I end up getting the map Phi sub 1. Okay, so that's the ordering that we are taking. E sub 1 comma Phi sub 1 is at most E sub 2 comma Phi sub 2 if first E sub 1 is a subfield of E sub 2 and second Phi sub 2 is an extension of Phi sub 1, meaning Phi sub 2 restricted to E sub 1 is Phi sub 1. In this diagram we can see it like this, that E1 is embedded into E2, and we have a map from E1 into f bar prime, that's we call Phi1, Phi sub 1, and we have a map from E sub 2 to f bar prime that we call Phi sub 2, and this diagram is a commuting diagram. Now, the first step is, why is this really a partial order on sigma? So the first step is to show that sigma with this relation is indeed a partially ordered set, a poset. Okay, so this means that I need to prove 3 properties for this relation. The first one, reflexive. Every pair E comma Phi is at most E comma phi, which is clear because E is a subset of E and phi restricted to E is phi. I'm not changing it. So that's clear. Now, next I'm going to argue why we have anti-symmetry. That means that if I tell you E sub 1 comma phi sub 1 is at most E sub 2 comma phi sub 2, and the reverse is also correct, E sub 2 comma phi sub 2 is at most E sub 1 comma phi sub 1, then I want to argue that they are the same pairs. Let's start with the first component, the sets, the subfields. Knowing that we have these relations, we can deduce that E sub 1 is a subset of E sub 2 and E sub 2 is a subset of E sub 1, and therefore they are the same fields. Now, knowing this condition means that phi sub 2 is an extension of phi sub 1. Knowing this condition, we have the other way around, but I mean, this is enough because E sub 1 is E sub 2. That means that phi sub 1 is phi sub 1 is phi sub 2. So that means that the pairs are the same. So this shows the anti-symmetry relation. Finally, we want to show the transitivity, the transitive property. So suppose the pair E sub 1 phi sub 1 is at most the pair E sub 2 phi sub 2, and the pair E sub 2 phi sub 2 is at most the pair E sub 3 phi sub 3. I want to show that the pair E sub 1 phi sub 1 is at most the pair E sub 3 phi sub 3. Let's start with the first component. Because of this condition, E sub 1 is a subfield of E sub 2. Because of this condition, E sub 2 is a subfield of E sub 3. Therefore, E sub 1 is a subfield of E sub 3. Now, because of the first condition, phi sub 2 is an extension of phi sub 1, but phi sub 3 is an extension of phi sub 2 because of the second condition. So phi sub 3 is an extension of phi sub 2. Phi sub 2 itself is an extension of phi sub 1. Therefore, phi sub 3 is an extension of phi sub 1. And so this implies exactly the transitivity condition. So we are working with a poset. And as I've indicated, we want to find a maximal element of this poset. By Zorn's lemma, this poset has a maximal element precisely when every chain has an upper bound. Okay, so we take maybe not precisely when, so by Zorn's lemma, in order to show that this has a maximal element, it is enough to show that every chain has an upper bound. So let's start with a chain. So C consists of this family of pairs E sub I and phi sub I. This capital I is some index set, and this C is a chain in sigma. Now I want to show that this chain has an upper bound. So this means I need to find a pair E comma phi, where E is an intermediate subfield and phi is an F embedding from E to F bar prime. That's our goal. So we start with the first component, E. I'm giving you a chain of subfields, and I need a subfield that contains all of them. Again, we are in the realm of this general philosophy that a union of chain of algebraic objects should satisfy the same algebraic property. So union of chain of subfields is a subfield. So that would be our subfield, the candidate for our subfield, union of E sub i's. And now again, how can I find this map? We are essentially gluing these phi sub i's together. That means in order to define this phi, I pick an element inside E. That means I'm picking an element inside one of these E sub i's. It can be in many of these E sub i's. But it's definitely in E sub I for some I. And then I ask myself, what does phi sub I do to this element, and call that guy to be phi of E. I need to justify why this is independent of choice of the index I, why phi is well defined. But after we do so, we get the desired pair, because as you can see here, this phi restricted to E sub I is phi sub I. That means the pair E comma phi would be more than the pair E sub I comma phi sub I. Or the pair E sub I comma phi sub I is at most the pair E comma phi. So that means the pair E comma phi would be an upper bound for the pair, for all the pairs E sub i's comma phi sub i's. E sub I comma phi sub i's. Okay, so that's our goal. So we want to show that this union is indeed an intermediate subfield. This map that we are defining is indeed well defined. It is an F embedding. And finally, E comma phi is an upper bound for the chain of E sub I comma phi sub i's. So this is our goal. This is step 2, the goal of step 2. Let's start with proving why union of E sub i's is a field. So let's pick 2 elements, A and B inside E. That means it is in the union of E sub i's. So A belongs to E sub I for some index I, and B belongs to E sub j for some index j. Without loss of generality, I can assume that, we are dealing with a chain. That means that E sub I comma phi sub I is at most E sub j comma phi sub j, or the other way around. So every 2 pairs in this chain can be compared with each other. So either one of them is less than the other one, or the other way around. Now, without loss of generality, I can assume that E sub I comma phi sub I is at most E sub j comma phi sub j. Now that means the first components, E sub I, should be a subfield of the first component of the other pair, E sub j. Now, A and B belong, A belongs to E sub I, B belongs to E sub j, so both of them belong to E sub j. E sub j is a field. That means A plus minus B times A times comma A times B plus A times B, or A divided by B, both of them belong to E sub j, because E sub j is a field. But E sub j itself is a subfield of E, the union. That means that all these elements belong to the union, which is E. So E is a subfield, because it is closed under addition, subtraction, multiplication, division. So it is an intermediate subfield of the extension F bar over F. Okay, next we want to show that the map phi is well defined. How can we show that phi is well defined? Again, let's start understanding the issue. The issue is that this map phi, when I want to define phi of E, I have a choice to make. I mean, there are many, possibly many, infinitely many indexes I that have this property, where capital E sub I contains the element small e. So which one do I want to choose? Which one do I want to pick? I pick one of them, and then I use what phi sub I tells me to do. Now the question is, what happens if I choose another I? Do I end up getting the same quantity for phi of E? After all, we want to define a well-defined function, so I need to assign only one value to E. Which one of these values am I assigning? I'm going to argue that all of them are the same, and therefore there is no ambiguity. So let's go back here. So for every E that you give me, suppose that I have two indices, I and j, where E sub I and E sub j, both of them contain E. So again, suppose E is inside both E sub I and E sub j. Since C is a chain, either this pair is at most E sub j comma phi sub j, or the other way around. Now, without lots of generality, I can assume that E sub I comma phi sub I is at most E sub j comma phi sub j. That means E sub I is a subset, is a subfield of E sub j, and phi sub j is an extension of phi sub I. Now, because E belongs to the smaller field, I can talk about both phi sub I and phi sub j. But phi sub j, when I restrict it to E sub I, is the same as phi sub I. So phi sub j of E is equal to phi sub I of E. That means that there is no ambiguity. So if I pick any index that I, so that E is inside capital E sub I, phi sub I does the same to E. We are going to get the same value, value in F bar prime. So the phi is indeed well defined. Now let's see why it is an F embedding. So we showed that phi is well defined. Now I want to show that it's a ring homomorphism. So let's pick two elements inside E. We have already discussed that whenever I pick two elements inside E, then it is in the union, then each one should be in E sub I, the other one in E sub j, but it's a chain. Therefore, we can assume that E sub I is a subset of E sub j, then, or the other way around. So that means that I can find some index I where both A and B are inside E sub I. Now, E sub I is a field. That means A plus B and A times B, both of them are also inside E sub I. Now, the way that we defined phi of elements, as soon as we find index I, we can apply phi sub I to that element. Because A plus B belongs to E sub I, phi of A plus B by definition is phi sub I of A plus B. But phi sub I is an F embedding. It's a ring homomorphism. So phi sub I of A plus B, and A and B, both of them are inside E sub I. So phi sub I of A plus B is phi sub I of A plus phi sub I of B. Now again, A and B are inside E sub I, so phi sub I of A is nothing but phi of A. And phi sub I of B is nothing but phi of B. So we got that phi preserves addition. By a similar argument, identical argument, we are showing that phi preserves multiplication. Again, A times B belongs to E sub I, so phi of A times B is phi sub I of A times B. Phi sub I is an F embedding. A and B belong to this field E sub I, so it is phi sub I of A times phi sub I of B. That's the same as phi of A times phi of B. So altogether we get that phi is indeed a ring homomorphism. Now, in order to show this ring homomorphism is an F embedding, it's enough to show, we have to show that when I restrict it to F, I get identity. For every A inside F, this belongs to every E sub I. No matter what index you pick, because E sub I is an extension of F, A does belong to E sub I, and then I can choose, then phi of A is phi sub I of A. But phi sub I is an F embedding, so therefore it is just A, which means phi restricted to F is identity of F, and that means that it is F linear. That implies that it is F linear. Now, finally, we notice that because E is a field and the map that we have is not the zero map, it is at least identity when I restrict it to F, then the kernel of phi should be trivial. It should be just zero, because in a field, we have only two ideals, the zero ideal and the entire field. And kernel of phi, because phi is not the zero map, kernel of phi is not the entire E, therefore it should be the zero ideal, which means phi is injective. So altogether, we end up showing that phi is indeed an F embedding from E to F bar prime. Okay, so this means that the pair E comma phi is an element of sigma. The way that we define this E comma phi, it is clear that for every index I in this index set capital I, E sub I is a subset of E, because E is the union of these subfields. And the way that we define phi, when I restrict phi to E sub I am getting phi sub I back. That means the pair E sub I, phi sub I is at most the pair E comma phi. That shows the second step. That shows that every chain in sigma has an upper bound. Therefore, I can use Zorn's lemma and deduce there is a maximal element. So sigma has a maximal element. Suppose L comma theta is a maximal element inside sigma. I want to show that L is precisely F bar. Okay, so suppose to contrary, this is not the case. So suppose that there is some element inside F bar which is not inside L. Okay. So we reach to the boundary of this kind of process of extension. We want to add alpha to this. We want to extend this theta to alpha as well and get a contradiction. Make the pair L comma theta even larger and reach to a contradiction. This is our goal. But how can I do it? Our bet would be using splitting fields and extension. Isomorphism extension result. Okay, so alpha is an element inside F bar. That means that it is an algebraic element over F, because F bar over F is an algebraic element. So that's the first thing. So alpha is algebraic over F. Now that it is algebraic over F, I can talk about its minimal polynomial. Now I'm going to use the other property of algebraic closures. Because F bar is an algebraic closure of F, it is algebraic over F and it is algebraically closed. That means every polynomial can be decomposed into linear factors. So I can decompose this into linear factors. I can find all the zeros of this guy inside F bar. That means the minimal polynomial of alpha over F, not over. Do I want to do it over F or? Okay, so here I'm working with L, so let's do it over L, sorry. I want to extend my map from L to this larger field. That's why it's better to work with L, but the reason that alpha is algebraic over L is because alpha is algebraic even over F. So I'm looking at the minimal polynomial of alpha over L, and then I can decompose this into linear factors in F bar bracket X. Now let's use the map theta that we have. Apply theta to alpha. Then I get, or I can apply theta to the entire minimal polynomial of alpha. So that would be the same as, okay, so it's better to say it like this. That I'm looking at theta of the minimal polynomial of alpha comma L, but this is the minimal polynomial of theta of alpha over theta of L. So all the coefficients of this polynomial belong to theta of L, and theta of alpha is a zero of this polynomial. Theta induces an isomorphism between L and theta of L. So theta of L is essentially L. It's a copy of L. Now, when I give you a minimal polynomial for alpha, after I apply theta, I get a minimal polynomial for theta of alpha. But now I use the fact that f bar prime is algebraically closed and deduce that this minimal polynomial can be decomposed into linear factors in f bar prime. One of them is theta of alpha. So altogether, we are finding these elements, alpha 1 dot alpha n in f bar, and alpha 1 prime dot alpha n prime in f bar prime, so that the minimal polynomial of alpha over L is decomposed into these linear factors, and minimal polynomial of theta of alpha over theta of L, which is the same as theta of the minimal polynomial of alpha over L, is also factored into these linear factors. Now let's consider L hat to be the subfield of f bar that is generated by L and alpha i's. And let's L hat prime to be the subfield of f bar prime that is generated by theta of L and alpha 1 prime dot till alpha n prime. And notice that these are the fields that are generated by the base fields L, respectively theta of L, and zeros of the minimal polynomials of alpha and zero of the minimal polynomial of theta of alpha over L over theta of L, respectively. So these are splitting fields of these polynomials over L and theta of L, not L prime, but rather theta of L. So we have this isomorphism from L to L to theta of L, which is induced by theta. Now, this isomorphism sends the minimal polynomial of alpha over L to theta of the minimal polynomial of alpha over L. And I'm taking the splitting fields of these polynomials over L and over theta of L, respectively. By the isomorphism extension theorem, we showed, or it was part of the uniqueness results of the splitting fields as well. We can always extend this isomorphism between the base fields to an isomorphism of these splitting fields. So there exists this theta hat, which is an isomorphism of these splitting fields, so that when I restrict this theta hat to the base field, I get theta back. That exactly means the pair L comma theta is at most the pair L hat comma theta hat. I have built up theta hat, I have extended theta and end up getting theta hat. And notice that the way that we have constructed it, now L hat contains alpha, which was not inside L. So this means this pair is not the same as the old one. It's a genuinely larger pair. But that's a contradiction, because the pair L comma theta was supposed to be a maximal element inside sigma. Now we found this pair L hat comma theta hat in sigma, which is larger than the pair L comma theta, and that gives us a contradiction because of this contradicts maximality of the pair L comma theta. So this means that if I give you a maximal element in sigma, then the field part is the entire F bar. That means we end up finding an F bar embedding, an F embedding from F bar to F bar prime. Now, next we are going to argue that this embedding is indeed an isomorphism. It is also surjective. So the claim is that there is an F isomorphism between F bar and F bar prime. So again, by the previous step, we have already found an F bar embedding from an F embedding from F bar to F bar prime. Let's call it theta. Because theta is already an embedding, that means that theta gives us an isomorphism between F bar and theta of F bar, the image of theta. Because F bar is algebraically closed, every field that's isomorphic to it is also algebraically closed. That means that theta of F bar, the image of theta, is algebraically closed. But every intermediate subfield of F bar prime, so F bar prime, is algebraic over F. So if I give you an intermediate subfield of F bar prime over F, F bar prime would be algebraic extension of that field as well. So theta of F bar is an intermediate subfield. That means F bar prime is an algebraic extension of theta of F bar. So F bar prime is an algebraic extension. But remember, theta of F bar is algebraically closed. One of the equivalent forms of saying that a field is algebraically closed is to say that there is no non-trivial algebraic extension. Now, this is an algebraic extension. It cannot be non-trivial. That means F bar prime is equal to theta of F bar. So that shows theta is both embedding and surjective. So theta is an F isomorphism that completes the proof of uniqueness of algebraic closures. So next we will see a few basic properties of algebraic closures. So for instance, one of the important results is that, so we can feel it, that algebraic closures are kind of largest algebraic extensions of F. How can we make it precise? So one way to formulate this is to say that if E over F is an algebraic extension, then there is a copy of E inside F bar. Okay, so let's again formulate it precisely. So suppose F is a field, F bar is an algebraic closure of F. Suppose E over F is an algebraic extension. Then I can find an F embedding from E to F bar. So every algebraic extension can be embedded into F bar. How can we do it? The next argument that this argument that I'm going to present is a kind of a good technique in order to send algebraic extensions to a fixed algebraic closure of a field. But pay attention to the first part of the proof. In the first part of the proof, we start with an algebraic closure of this algebraic extension. And we are going to show that algebraic closures of algebraic extensions are again algebraic closures of the base field. So E bar is an algebraic closure of E, this extended field. But then we are going to show, we are going to argue that this algebraic extension of this algebraic This algebraic closure of this algebraic extension is an algebraic closure of the base field itself. So we are going to show that E bar is an algebraic closure of F. What does that mean? This means I need to show E bar over F is an algebraic extension and E bar is algebraically closed. The fact that E bar is algebraically closed is clear because we know E bar is algebraic closure of E. So the part that E bar is algebraically closed has nothing to do with the base field that we have chosen. But the other part is important. Why is E bar over F algebraic? E bar over F is a tower that consists of two blocks, for instance, E bar over E and E bar and E over F. E bar over E is an algebraic extension because E bar is an algebraic closure of E. E over F is algebraic by hypothesis. Now, a tower of field extensions where all the blocks are algebraic gives us an algebraic extension from the top to the base. So E bar over F is an algebraic extension as we wanted. That implies that E bar is indeed an algebraic closure of the base F. Now, by the uniqueness of algebraic closures, there is an F isomorphism from E bar to F bar. Now I can restrict it to E and get an F embedding from E to F bar. And that completes the proof of this proposition. So an algebraic closure of a field contains a copy of every single algebraic extensions. So you see the importance of understanding F bar over F. Because if I kind of understand F bar over F, then if I have enough tools to understand F bar over F, then I can understand all the algebraic extensions of F. So then I can understand all the zeros of the polynomials. So these understandings, and the word understand, it's quite vague, but it should motivate us to investigate the extension F bar over F further. So the next thing that we want to understand, okay, we want to understand the extension of F bar over F. What kind of extension is it? We will show that it is always a normal extension. In fact, this is rather easy. Now the question is it a Galois extension? And the answer is it is Galois if and only if the base field is a perfect field. And recall that a field is called perfect if either characteristic is 0, or if characteristic is positive, it's a prime number P, then the Frobenius map is an isomorphism. And it's clearly embedding, so it's enough to show that it is surjective. So alternatively, sometimes we write that F to the power P is F. The precise way of saying is to say that the Frobenius map from the field F to itself, which sends A to power P, is an isomorphism. So if we have these properties, we say the field capital F is a perfect field. And here we want to show that the extension F bar over F is a Galois extension if and only if F is a perfect field. Okay, let's start with why this extension is always a normal extension. What does normal mean? Normal means that every element that I give you inside this larger field, then the minimal polynomial can be factored into linear factors. Okay, so let's pick an element inside F bar. F bar is algebraic, so that means I can talk about the minimal polynomial. F bar is algebraically closed, so every polynomial can be decomposed into linear factors. In particular, the minimal polynomial of alpha over F can be decomposed into linear factors. So I can find alpha 1 dot alpha n inside F bar and decompose the minimal polynomial into linear factors, and that's it. So that means that the extension f bar over f is a normal extension. Now let's see why knowing that it's Galois implies that it is perfect. If the characteristic is 0, there is nothing to show. So let's assume that the characteristic is P. And I want to show that it is perfect. That means that I need to show every element A inside the field capital F is a power of P of some element. So for every A inside F, I can write this as alpha to power P for some alpha inside the field capital F. So I pick this A. I want to write it as some alpha to power P. Maybe I cannot do it inside F, but I can definitely do it inside F bar, because F bar is algebraically closed. The polynomial x to power P minus A has a 0 inside F bar. Let's call the 0 to be alpha. This means alpha raised to power P is A, so x to the P minus A is x to the P minus alpha to power P, and I can use the fact that it's characteristic P and write this as x minus alpha raised to power P. So that means that the minimal polynomial of alpha over F should divide the polynomial x minus alpha raised to power P, because alpha is 0 of this polynomial. So that means it is x minus alpha raised to some power. But on the other hand, f bar over f is supposed to be Galois. That means it's supposed to be a separable extension. So the minimal polynomial of elements inside f bar cannot have multiple roots. So this does not have multiple zeros in a splitting field of over the base field. But it is supposed to be x minus alpha raised to some power. It doesn't have multiple zeros, so the power should be 1. So the minimal polynomial of alpha over f is just x minus alpha, which means alpha is indeed inside f. So altogether, we end up writing A as alpha raised to power P for some alpha inside f, which means that the Frobenius map is surjective, and therefore it's an isomorphism. Okay, so now let's go backward. Assume that my base field is a perfect field. I want to show that f bar over f is a Galois extension. If the characteristic is 0, we have already discussed that every algebraic extension would be separable. So in that case, f bar over f would be a separable extension. We have already proved that f bar over f is always a normal extension, and so f bar over f is a Galois extension. Now, we are going to focus on the case that characteristic is P, a prime number. Again, I need to show that f bar over f is separable to finish the argument, because we already know that f bar over f is a normal extension. So we are going to show that f bar over f is a separable extension. And that means I need to show for every alpha inside f bar, the minimal polynomial of alpha is a separable polynomial. So I pick an alpha inside f bar, I consider its minimal polynomial, and I need to show that it is separable. But we have proved that no matter what polynomial I give you, whenever I give you an irreducible polynomial, we can find a separable irreducible polynomial and write this polynomial as this separable irreducible polynomial of x to power p to the k for some positive integer k. For some non-negative integer. K. It can be 0. We want to show that k is 0, and from there, this p to the k disappears, and we end up getting that the minimal polynomial is this separable polynomial, and that finishes the proof. That shows that the minimal polynomial is indeed separable. So this polynomial S is a separable polynomial in f bracket x. And because the minimal polynomial is a monic polynomial, this polynomial is also monic. So let's assume that coefficients of this polynomial, this separable polynomial, are denoted by c sub i's. So it is x to the m plus c sub m minus 1, x to the m minus 1, and so on. These coefficients belong to f. Now, f is a perfect field. That means every element inside f can be written as something raised to power p. So c sub i's can be written as d sub I raised to power p. So for every index I, c sub I is d sub I raised to power p. I'm going to substitute d sub I to power p for c sub i's in this summation over here. So this means that, and then I'm going to use the fact that the minimal polynomial is essentially this summation, but instead of x, I'm going to substitute x to power p to the k. Altogether, we get that the minimal polynomial of alpha over f is x, instead of x to the m, I have to write x to the power m times p to the k. Instead of c sub m minus 1, I have to write down d sub m minus 1 raised to power p. Instead of x to power m minus 1, I have to write down x to power m minus 1 times p to the k minus p to the k. And then the next term, similar. Then the one before the last one, I have to write down d sub 1 to power p instead of c sub 1. Instead of x, I have to write down x to power p to the k. Instead of c sub 0, I have to write down d sub 0 raised to power p. Now, if k is a positive integer, then all these terms are something raised to power p. Now, because characteristic is prime p, I can pull out this power p and write this as x to power p to the k minus 1, taking out one of the p's out. Instead of d sub m minus 1 raised to power p, I just simply write d sub m minus 1, and then take one of these powers out, one of the p's out, and continue like that. Instead of d sub 0 to power p, I will just write down d sub 0. Remember, d sub i's belong to f. So this guy, the polynomial inside the parentheses itself is a polynomial inside f bracket x. So altogether, we end up writing the minimal polynomial as a polynomial inside f bracket x raised to power p. That's not possible because the minimal polynomial is irreducible in f bracket x. That's a contradiction. Why did we get a contradiction? We got a contradiction because of this assumption over here. Because here, innocently, I assume that k is positive. That gave us a contradiction. So k cannot be positive. So k is 0. That means that the minimal polynomial of alpha over k over f is separable, is this separable polynomial that we had. So it's a separable polynomial, and that's exactly what we wanted to show. This implies that the extension f bar over f is a separable extension. We have already showed that this is also a normal extension. This completes the proof. Now, an immediate corollary of this is that a field is perfect if and only if every algebraic extension is separable. So a field f is perfect if and only if every algebraic extension is separable. Let's go with why perfect implies that every algebraic extension is separable. Again, this is an argument that we had earlier, that if E bar is an algebraic closure of this algebraic extension E, then E bar itself is also an algebraic closure of the base field f. This argument we had earlier, and the whole point is that E bar is already algebraically closed. We only need to argue that E bar over f is an algebraic extension, and this is the case because both of these blocks, E bar over E and E over f, are algebraic. And tower of algebraic extensions is an algebraic extension. So E bar is an algebraic closure of f. F is a perfect field. Therefore, E bar over F is a Galois extension, because we showed that when F is a perfect field, then the algebraic closure over the extension that's coming from an algebraic closure of the base field over F is a Galois extension. So E bar over F is Galois. E bar over F is a separable extension. So therefore, every intermediate subfield that I pick, both of the blocks are separable extensions. So E bar over F is separable. E is an intermediate subfield of this. Therefore, E over F is a separable extension. That completes the proof of this corollary. This direction. So the other way is immediate, because we are assuming that every algebraic extension is going to be separable. Now I'm going to take an algebraic closure of the base field. That gives us an algebraic extension. By hypothesis, this extension is separable. This extension is already proved to be a normal extension. So therefore, this is Galois. We prove that F bar over F is Galois if and only if F is perfect. That completes the proof. Okay, so next, we want to use this intuition that I've mentioned repeatedly earlier, that F bar can be viewed as union of intermediate subfields that are splitting fields of polynomials over polynomials in F bracket X. So I've mentioned this, but I did not prove it. So let's prove this statement, that if I look at splitting fields of polynomials in F bracket X and take their union, I end up getting my algebraic closure. Okay, so that's my goal. So suppose F bar is an algebraic closure of F. I'm going to denote the set of intermediate subfields of F bar over F that are finite and normal by this notation. So int for intermediate, F for finite, N for normal. So int sub F comma N of F bar over F denotes the set of all the finite normal extensions. Remember, an extension is a finite normal extension if and only if it's a splitting field of some polynomial. So I'm essentially working here. This set is the set of all the splitting fields of polynomials over the base field, capital F, that live inside F bar. Now, claim is F bar is the union of these intermediate subfields. Okay, so let's pick an element inside F bar. That would be an algebraic element over F, because F bar over F is algebraic. But F bar is also algebraically closed. So that means every polynomial that I give you, including the minimal polynomial of alpha over F, can be factored, can be decomposed into linear factors. And that means I can find alpha i's inside F bar and write down the minimal polynomial of alpha over F as product of x minus alpha sub i's. So I can write this down, and alpha is also a 0. I can assume that the first 0 is alpha, then alpha 2, and the rest inside F bar. Now I'm going to look at the subfield generated by the base field and the zeros in order to get a splitting field of a polynomial. So E is a splitting field of the minimal polynomial of alpha over the base capital F. As I've mentioned, an extension is a finite normal extension if and only if it's a splitting field of some polynomial over the base field. So that means E over F is a finite normal extension. So this means E does belong to this set. But alpha is an element inside E. You see alpha 1 is alpha, and alpha is inside E. So this means that every element of F bar is inside this union. It belongs to one of these intermediate subfields. So that shows that algebraic closures are indeed union, in certain sense, union of splitting fields of polynomials in F bracket X. Now, notice that F bar over F is a normal extension. if E is one of these finite normal extensions, again, E over F is also a normal extension. So I can use the restriction map. And the restriction map would be a surjective map. So this comes from the isomorphism extension theorem that says that because E over F and F bar over F, both of them are normal extensions, then the restriction map is a well-defined group homomorphism from the F automorphisms of F bar to F automorphisms of E. So this R sub E is just taking theta, restricting it to E. We have proved that because E over F is a normal extension, it's well defined. The image of theta of E is E still, so it's well defined. And we also proved the isomorphism extension theorem, which implies that this map is indeed surjective. So the isomorphism extension theorem by itself cannot be applied here. And the isomorphism extension theorem was true only when the F bar over F was also a finite extension. But by the uniqueness result, so you see we have that F bar over F bar. So I have, so we have to have this kind of a extension result that we have over here. So meaning F bar can be viewed as an algebraic extension, algebraic closure of E, and we have a map from E to E. I want to say that it is surjective, so let's assume that this is an isomorphism. This uniqueness result that we proved over here, I'm not going to redo it again, but you can use this line of argument and in fact prove this more general statement. Instead of just showing that there is an F isomorphism between these two, I can say that if I give you theta bar, an automorphism of F, then there exists theta from F bar to F bar prime, that is isomorphism, and when I restrict theta to F, theta to F, I get theta bar. The proof that we gave here is when theta bar is identity. So we showed this when theta bar is identity, but if you go through the argument, you see that the same argument works. The only difference is that instead of saying F embedding, we have to demand that a phi restricted to E, restricted to F, should be theta bar. So if instead of saying that it is F embedding, we say this, then we can run through the same argument and deduce this slightly stronger result, which can be viewed as an isomorphism extension theorem. From F to F, we can extend it and get an isomorphism from from one of the algebraic closures to another algebraic closure. So this is a kind of ultimate isomorphism extension theorem. So I leave it to you to show this isomorphism extension theorem for algebraic closures. It's essentially part of your homework assignment. Now, if you run that, you get surjectivity of this group homomorphism as well. So the fact that it is well defined, we have already proved long ago, because F bar over F and E over F, both of them are normal extensions. Surjectivity, we showed it only when the first one was a finite extension as well. Here we don't have that, it's a finite extension, but nevertheless, because of the way that we proved uniqueness of algebraic closures, we can extend that and get this ultimate isomorphism extension theorem. And from there, we can deduce surjectivity of these group homomorphisms. Now that these are surjective, we get these kind of pictures as well. Now, if I also give you two intermediate subfields that are finite normal extensions, and one of them is a subfield of the other one, then this time, in fact, we have already proved that this restriction map is a surjective group homomorphism because both of them are finite normal extensions. We have already proved that this is a well-defined surjective group homomorphism. So I can capture these information in the following diagrams. I have F bar. Inside F bar, I have E primes, and inside E primes, I have E. If I start with theta, I can restrict it to E prime and E, or I can restrict it from E to E prime. So I get this kind of trivial equality. So alternatively, I have this top group, large group, and I have these finite groups. These finite groups are quotients. We have onto maps from this large group to both of these finite groups. From this finite group to the other one, I have also an onto map that comes from the restriction map. And these maps are compatible with each other. So this means that this diagram is a commuting diagram. This means exactly this equality. I can restrict it to E prime and then restrict it to E, or I can directly restrict it to E. I get the same result. Now I can put these restriction maps together and get a function from this large group of symmetries of F bar over F to the product of these finite groups, group of symmetries of splitting fields or finite normal extensions, intermediate subfields that are finite normal extensions. So all these groups are finite. I'm taking product of these finite groups and I'm giving you a function from this large group to the product of these finite groups, essentially by restricting theta to E. Because these things are group homomorphisms, this R is going to be a group homomorphism. Now, next I'm going to argue that R is an embedding. So suppose theta is in the kernel of R. That means that when I restrict it to E, its identity of E, no matter what intermediate normal finite extension I pick for every finite normal extension of E. But remember, F bar is the union of these finite normal extensions. So if theta restricted to every one of them is identity, this means that every element inside F bar is sent to itself, because every element here is inside one of these, and every element here is sent to itself. So this means that theta is identity. So kernel of R is trivial. That means R is injective. Now I want to understand image of R. When I look at image of R, I get R of E or RE prime theta. So if E prime and E are, if we can compare them, if one of them is a subset of the other one, then there is a compatibility between these components. They should be compatible with each other, meaning when I restrict one to the smaller subfield, I have to get the other component. So let's put these kind of elements together. So consider those theta sub e's. You see, I'm working with the product. I want to understand the image. So I'm working inside this direct product of these finite groups. Now, in this direct product, I consider those elements that have this kind of compatibility property, that if E is a subset of E prime, is a subfield of E prime, both of them are finite normal extensions inside this F bar, then when I restrict the component associated to E prime, from E prime to E, I get the component for E. There is this kind of compatibility between these automorphisms. These kind of compatible elements of this direct product we denote by G of F bar over F. And the proof, I mean, the claim is that this is precisely the image of R. This is your homework assignment, so I will just give you the outline. What is this? What is this theta that is sent to this theta E's? I need to show that it is surjective, so I need to find this theta that when I restrict to E, I end up getting theta of E. So that's how we define theta. So we let theta from F bar to F bar to be defined like this. For every alpha inside F bar, this alpha belongs to one of these E's because F bar is the union of these finite normal extensions. So I can find some E that contains alpha, and then I use theta of E and apply it to alpha. And I let that guy to be theta of alpha. I need to show that theta is well defined, but that one should be okay because we know these theta sub E's are compatible with each other. So that can help us to show that theta is well defined. As soon as we show it's well defined, it is easy to show that it is a homomorphism, because if I give you alpha and beta inside F bar, then I can find a finite normal extension that contains both alpha and beta. Essentially, by looking at the splitting field of the minimal polynomial of alpha times minimal polynomial of beta, I find a finite normal extension that contains both alpha and beta. Then I can apply the fact that theta of E is a homomorphism and deduce that theta is a homomorphism. Now, theta is a homomorphism, but the restriction to F is trivial, is identity. So it's an F linear map. It's from a group to group, so it is injective. And it sends E to E, all in the image of theta. I do get the entire, in the image of theta, I get image of theta E's. So every finite normal extension is in the image of theta. So that implies that theta is also surjective, and therefore it is an automorphism. And finally, the R of theta is in this, and that gives us that everything inside G F bar over F is in the image. So altogether, we get that the group of automorphisms of F bar over F is isomorphic to this strange-looking subset of the direct product of these finite groups. So this strange-looking subset is called inverse limit of these finite groups for now.